So, hello everyone, my name is Stylianos Karagiannis. I'm from PDMFC, based in Portugal. So I will present today the Security Information and Event Management System, or also SIEM. To begin with, the SIEM component is responsible for triggering the alerts, collecting data from log files, from multiple resources like the DTM, system log files that are provided on host operating systems, from Windows machines, from Linux machines, any log files that are collected. And these data are actually parsed on the SIEM in order to aggregate data and by using a condition system to raise alerts. The data can be either constructed data, meaning JSON files from log files, CSV files, or can be even raw text files, meaning that if there are unconstructed text files and there is a symmetry inside these text files, this can be parsed on the SIEM by using regular expressions. The SIEM continuously monitors the events that are created from the log files and trigger the alerts according to the scheduled queries, as we call on the SIEM. And the alerts could include executions of bash scripts, shell scripts on another computer, for example, or to send an email if an alert pops up, or to have API calls to other external software or services, or to publish Kafka information to Kafka topics regarding the alerts. The novelty on that is that we go beyond the detection, and it's possible actually from the SIEM to execute bash shell scripts or have API calls, post methods to other components in order to interact with the attacks. Let's have a use case for the SIEM just to explain more about how this works. This will include also some information about other components, how these components are useful on the incident response. Here we can have an example use case. It's a generic use case. We have a worm inside a laptop, a normal personal computer. And this worm creates like a lot of traffic and goes on a denial of service attack. And there are multiple entities inside the network, like a PC2, a computer, or another computer. Some of these computers could have vulnerabilities. For example, the personal computer 2 might have vulnerabilities, serious vulnerabilities, while the other does not. So the vulnerability scanning actually monitors the vulnerabilities. If this computer executes the worm, then it creates a lot of traffic inside the network. So the DTM actually captures this data. And also we have the SIEM alerts are popping up according to these log files. All of them, the information that are retrieved by other computers or from the network are aggregated internally on the SIEM, and according to scheduled queries which are developed by the SOC analysts, it's possible to raise alerts and also to send data to other components like the RCRA, as we call it on the SPHINX, because it's about the risk. And this information could actually improve the total security awareness of the hospital, the hospital. So let's go here. So I explained how the use case could work on the SIEM side. I will get to more details afterwards. So we can see an overall diagram of how the SPHINX components are interacting, meaning that the SIEM is somewhere here. We have Kafka topics as a main central database for the reports to be published, and the SIEM actually subscribes to this Kafka topic. So it's like we have three different options to retrieve data. One is to collect data from the Kafka topics raised by other components. We can have our own agent to collect log files directly from host machines. And we can actually have also API methods for any other external component to send data to the SIEM. The CM, as other components as well, is not, you know, a specific tool, one component for everything. It splits to a different, large number of subcomponents, meaning that all the development right now is going as microservices. And the overall project actually of the SPHINX is based on that approach to be developed as microservices components. Here we can see some examples of how we collect data on the CM. We developed an agent as well to collect data directly from host machines. And you can see that we can collect metrics like the CPU usage, the disk usage, any connections. We can have we can retrieve network traffic and parse them to the CM. We can parse databases. We can collect everything, anything that we want. For example, the first one, it's about the CPU usage. So we were focusing mostly on Bitcoin miners or you know, cryptocurrency miners that are like Trojans or malware inside the machines that could cause high usage of CPU and so on. Here is an example on the CM side, how we can parse a CSV file containing a log file like this, I think, is network traffic. So it's like a source and destination IP, the source port which was used, and the UDP connection. So you can check that by using a CSV file. Of course, this is a structured file, it's not unconstructed. We can actually extract the tags, and then we can say that, okay, if there is a specific protocol, then Lda alert will trigger. So we can monitor and say that only specific protocols are allowed, and if there is another protocol running on the network, then we trigger an alert. Here it's how we parse again the data, and these are the three different options that we can actually have a listener. We name it as a listener because the listener actually waits and receives data from other components. We can either have an HTTP connection, a TCP connection, subscription to a Kafka topic, or we can also have an agent connected to the CM. Here, for example, you can see the MetaGo agent is the name of our agent. So the MetaGo agent actually runs and executes on a host machine, retrieves text files, log files, JSON files, network traffic, anything that we want. And all these data are parsed on the CM. You can see here again, here's from network traffic. Actually, we capture network traffic and parse it to the CM directly. All these data are stored on the indexes. We currently use Elasticsearch for a database. And here it's an example of a brute force alert. It's scheduled query which captures authentication failure. So if someone tries to do a brute force attack and tries more than 20 minutes for it, inside 20 minutes to do an authentication failure and tries a lot of passwords, then an alert raises and says that, okay, there is a lot of a large number of the authentication failures. So this could be a brute force attack, a password attack actually. Here we can see that the alerts which can be raised from the CM could be sent by email as a report. It could react to another component API. It could execute a shell script. It could publish on a Kafka topic, the alerts, just the alerts to be published on the Kafka, or to pin to an internal dashboard. So the CM holds an internal dashboard. Of course, on the SPHINX side, we use the interactive dashboards as the main dashboard of the project, but internally the CM actually has an internal dashboard system. Here's an example of an email sent by the CM of a specific alert that was raised. For example, that, okay, this username account tried to access a lot of different IPs, so it could be like a malicious guy that tries to pivot along the network. Here is also an example of a virus total alert, meaning that we can collect log files from a virus total about malware scanning, and this could be sent on the CM and have an alert if there is a virus alert. All these can be sent to an external API, as explained before. Here it's also an example how we publish on Kafka topics. Of course, we can change the tags. You can see here that if there is a priority level, then we can have another name if it's required by other components. So we can rename the tags actually that are captured by the CM. Okay, going. Here we can see an initial dashboard. Of course, we did not focus on creating a lot of complex dashboards on the CM side right now, because we rely on the interactive dashboards, but is something that we intend to do to improve our own dashboard inside the CM. Here is a parser of a text file, which was unconstructed. So you can see that if you have a text file that has a timeline, and then there is a symmetric space between the data, then we can extract them by using regular expressions and say that, okay, the second column could be the user, this one could be the action, this could be the PID, and all of these are extracted by tags. And actually, we can use afterwards conditions in order to check, for example, if a username other than this one appears, then raise an alert. Here it's another example how the rules are set. I don't get into deep details. Here is a table about the alerts. It was coming from Suricata internally, so the CM retrieved the fast or if.log from Suricata and actually parsed them inside the CM. We can combine this data with other log files and make something like a more comprehensive alerting system. We can build the deployment options are, of course, always we can build as a Docker. We can set it up on a Kubernetes, so that's the normal and regular way to deploy microservices. Here are the microservices that we use internally of the CM. Here is an example of the deployment of a Docker by using a Docker file, and that's it. Thank you.